I felt like I better go ahead and work the problems myself to ensure that that was the case. 81 plus x squared quantity squared. Oh, I did forget to put what I said I would put on. I can just put it on the board. It was actually Stephen's fault. Whenever he said, I don't think I could know all the trig substitutions, I thought, I better put it on there. But now, hopefully, you're saying, I don't need you to put it on the test. Yes, I've already agreed to do it, so I'll put them on the board. But anytime you see a plus sign in there, you know it's an a tangent theta. If it's a variable squared minus a constant squared, it's a secant theta. If it's a constant squared minus a variable squared, it's a sine theta. No problem. So in this one, I know it's a tangent, and that tangent function, a, or a squared, is 81. So x is going to equal 9 tangent theta. And then you say, well, if x is 9 tangent theta, then the derivative of x is 9 times the derivative of the tangent of theta, which is secant squared theta with respect to theta. So now I can say, okay, x equals 9 tangent theta. At the same time, I'll also go in and simplify out what is 81 minus x squared then. I can say, 81 plus x squared. 81 plus x squared would be 81 plus 9 squared, 81 tangent squared theta. And I can see, well, this is nothing more than 81 times 1 plus tangent squared. We know that 1 plus tangent squared is secant squared, so this is 81 secant squared theta. So I plug this into my formula, and I'll say, okay, all of this makes the integral dx. Here's dx, 81 secant squared theta d theta. 9 secant squared theta d theta. My denominator, though, is going to be 81 secant squared theta quantity squared. Now, when I was doing this, I was kind of thinking of it, well, this denominator then is going to have an 81 times an 81. This 9 can cancel out with one of these 81s and leave a 9 down here in the denominator. 9 times 81 is 729. So I went ahead and I factored out a 1 over 729 just to get rid of that constant in there. And then I'm left with the integral. Well, I'd have secant squared in the numerator, but I have secant to the 4th in the denominator. That's going to give me secant squared over secant to the 4th is 1 over secant squared. And then you're thinking, but 1 over secant squared doesn't look nice. So the reciprocal of secant is cosine. This is equal to 1 over 729 on the integral of cosine squared theta d theta. And then, if you don't have it memorized, you could use the formula that I do put on the sheet. Power reduction formula for the cosine function is 1/2 times 1 plus the cosine of twice the angle. So I could say that 1/2, that's got to be part of this. I can bring out front, it's going to multiply this 1 over 729. That will give me 1 over 1458 on the integral of 1 plus the cosine of twice the angle. Be careful and don't write that as cosine squared theta. Now it's cosine of 2 theta with respect to theta. Both of these terms are easily integrable, so we do it. I'll have my 1 over 1458 on the outside. When I integrate 1 with respect to theta, that's theta. When I integrate the cosine of 2 theta with respect to theta, the integral of the cosine is the sine. And then when I integrate an angle of 2 theta, I've got to divide by that 2. So this is going to be 1/2 the sine of 2 theta. Plus the constant of integration. And so I can say, well, okay, I've got my 1 over 1458 on the outside. I think I'm going to leave it on the outside. My interior part has theta. It needs to be put back in terms of x. Here's where we take our formula in the problem. X equals 9 tangent theta, so x over 9 is equal to the tangent of theta. That allows me to draw a trig triangle. Here's theta. Tangent of theta is opposite over adjacent. Opposite here is x. Adjacent is 9. Thus, the hypotenuse is just going to be the square root of this leg squared plus this leg squared, x squared plus 81. Or, just to keep this format, I'll say it's 81 plus x squared. It does not matter. Now, I go back into my problem and I can say, well, okay, what is theta then? I know that the tangent of theta is x over 9. So theta is going to be the inverse tangent of x over 9. Now, the problem with this next term, and I didn't put this on the test, I don't believe, though it's not hard, the sine of 2 theta. I don't have an angle 2 theta. I know what the sine of theta is. I don't know what the sine of 2 theta is. So you have to use that double angle identity. The sine of 2 theta is equal to 2 sine theta cosine theta. Which means, hey, 2 sine theta cosine theta times this 1/2. This 2 and that 1/2 eliminate. So I can say, oh, this is nothing more than theta plus sine theta cosine theta. Yes. So sine theta, that's going to be opposite over hypotenuse, x over the square root of 81 plus x squared. That's the sine of theta, times the cosine of theta, adjacent over hypotenuse, 9 over the square root of 81 plus x squared, plus c. And then at this point in the problem, I saw that some nice cancellation was going to occur. So I decided to distribute the 1 over 1458 to both of the terms. 1 over 1458 inverse tangent of x over 9. And 9 will go into 1458 because I know 1458 was nothing more than 729 times 2. 729 was 81 times 9. So this is going to be nothing more than 81 times 2, 162 when it cancels with a 9 in the numerator. That would be my fraction out in front times the equation, or sorry, times the fraction, 1 times x. I'll just go ahead and put my numerator as x. And my denominator, and that should not be an equal sign, I apologize. It should be a plus sign. 162 times this square root times itself, that's just the group 81 plus x squared. Plus the constant of integration. Final answer for 11. Now, I hope you're thinking, that's not bad.
It wasn't bad until about, 1 over 145.
Yeah. And I would have been fine with this answer. The other answer is better, of course. Now, number 12 is harder than the number 12 I put on the test. And I know I've said this before, I think you'll be disappointed with the difficulty level of the test. Disappointed in saying, wow, he was too easy on us.
Probably not.
If you think it's harder, yeah, you've got a problem.
We knew that already.
It is not. The integral of dx over x squared minus 36. So I'll even say this. I kept the trig substitution problems in the same order. So you automatically know, oh, the first trig substitution problem I come to, I'm going to use a sine theta. Then I'll use a tangent theta. Then I'll use a secant theta. Yes. I didn't even change the order. Gosh, John. To the 3 over 2 power. You're like, okay, so how do I work this problem? You just say it's a constant taken away from a variable. Every single time it's in that order, the substitution is going to let x equal a secant theta, where a squared is 36. So a is 6. 6 secant theta, which tells you dx, derivative of 6 secant theta, is going to be 6 times secant theta tangent theta. D theta. So now in my numerator, yes, go ahead.
Don't ever forget to do the dx part.
Oh, right, yeah. You got to do that. Did you do something without it?
I think that quite possibly I may have run into half of the problems I ran into because I was forgetting to
Didn't
do
put
that.
the dx, yeah. And if you don't put the dx, you might think, well, I bet it makes an easier problem. It makes a much more difficult problem because you don't have terms that cancel out like the way these do. So yeah, make sure you do the dx. Over here, I'll say, I know x is equal to 6 secant theta, so x squared minus 36 is going to be 36 secant squared theta minus 36, which you know is just going to be 36 times secant squared theta minus 1. Secant squared theta minus 1 is tangent squared theta. This is 36 tangent squared theta. So now I come back over here and I plug this into my formula, and I'll say it is a formula. It's an integral. The numerator dx becomes 6 secant tangent d theta. My denominator, I'm thinking, well, if I have x squared minus 36 to the 3 over 2 power, it's going to be this group to the 3 over 2. When I think, what's 36 to the 3 over 2 power? The square root of 36 is 6. 6 to the 3rd power is 36 times 6, 216. So I'd say this is going to equal 216 tangent cubed. So now I put that over here. And I know that the 6 over 216 reduces to 1 over 36. I'll pull that to the outside. Now, on the interior of this, I know that my numerator has a tangent that can cancel out with one of the tangents in the denominator, and it will leave tangent squared. And it has a secant that does not cancel out. So at this point, I can say, well, I wouldn't want to do a u substitution because the derivative of tangent is secant squared. I don't have that. Exactly. So now, but what I said first, that's the first thing I would look for. I would say, could I let u equal that denominator? And if the numerator was secant squared, that would be beautiful. But it doesn't work in this case. So I can say, okay, I know that secant theta over tangent squared theta, this is just scrap work, trying to simplify it. This is equal to 1 over cosine theta times, well, it's being divided by tangent squared, which is sine squared over cosine squared. But if you divide by a fraction, you multiply by the reciprocal of that fraction. Reciprocal of tangent squared would be cosine squared over sine squared. And you see some nice cancellation does occur here. Cosine's going to cancel out with one of these cosines. And you'll say, well, this is just equal to the cosine of theta divided by the sine squared theta. Now substitution does work beautifully. I can say this is 1 over 36, the integral, cosine theta over sine squared theta. When I'm looking at the denominator and say, well, the derivative of sine is cosine, so a u substitution now would be nice. Let u equal the cosine of theta. Sorry, sine of theta, not cosine. du is going to be cosine. Then the derivative of u is going to be the cosine of theta with respect to theta. So I know all of this just becomes du, and I'll get this is equal to 1 over 36 on the integral. It would be 1 over u squared du. I would rather write that as u to the negative 2 du. And then, guys, we can just use the power rule. So the integral of u to the negative 2, this is going to be 1 over 36 times u to the negative 1 over negative 1 plus your constant of integration. Well, u to the negative 1 over negative 1, that's just the power rule on this. I know u to the negative means the u belongs in the denominator, and it's going to be a negative. So I can say this is negative 1 over 36u plus c. Now, u is equal to the sine of theta, so I said, well, this is negative 1 over 36 sine of theta plus c. But now you're saying, well, you can't leave your answer in terms of theta. Of course not. So I go back up here and I say, I need a trig triangle. X is equal to 6 secant of theta. So I can say x over 6 is the secant of theta, which means the cosine of theta is the reciprocal 6 over x. I'll draw my trig triangle here. Here's theta. The cosine of theta is adjacent over hypotenuse. 6x. My remaining leg has to be the square root of the hypotenuse squared minus the other leg squared, square root of x squared minus 36, which I knew that had to pop back up into my problem. It had to. So I'll say, okay. My answer was supposed to be negative 1 over 36 sine of theta. So now I can say negative 1 over 36 sine of theta. Here's theta. Sine is opposite over hypotenuse. Square root of x squared minus 36. All over x plus c. Now, what I was thinking is I didn't like the looks of this answer with a fraction in the denominator of a fraction. So all I would recommend doing is, hey, let's just multiply by x in the numerator and denominator of this term. It's going to give me negative x over 36 on this square root. That just looks so much better. So that's 11 and 12. 11 and 12 are quite a bit longer problems than 13 and 14. 13 and 14 is pretty quick. Are we okay with those? All right, 13. So 13 is method 1 of partial fractions. And we know it's really more of an algebra problem than it is a calculus problem. So when I look at this and I say, I want us to integrate the integral of 3x over x squared plus 2x plus 8. Sorry, minus 8. With respect to x. Right now, I can't do that. There's no method of what I know other than partial fractions that can attack this. The derivative of the denominator would be 2x plus 2. That's not going to work with that numerator. It just doesn't. So substitution would fail miserably. But partial fractions works easily. All I do is I'll look at this fraction and I pull it down here. I'll say, well, let's simplify it. 3x over x squared plus 2x minus 8. First thing I want to do is factor that denominator. And I'm thinking, well, I know that the leading term is both x and x. Then I'm looking for factors of negative 8 that sum to be a positive 2. Well, positive 4 and negative 2. Multiplies to negative 8, adds to 2. Once I do that, once you realize your denominator is just linear factors, every single solitary time you'll break this apart. This is called partial fraction decomposition. You'll decompose this into say, well, it's some constant over this linear factor, a over x plus 4, plus b over x minus 2. Then at this point in the problem, you just say, okay, here's my equation. Take your equation, multiply by the least common denominator. So I'm going to multiply everything by x plus 4, x minus 2. Since it's an equation, we can do that. This will give us on the left just 3x. On the right, you'll see a times this x plus 4 and this x plus 4 cancels. You'll have a times x minus 2. Then you'll have plus b times this x minus 2 and this x minus 2 cancels. You'll have b times x plus 4. So now at this point, if you wanted to solve for b, what value of x would you put in to get rid of a? 2. There you go. So I'd say let x equal 2. 3 times 2 is 6. It's going to be a times 0 plus b times 2 plus 4, b times 6. This is giving me 6b is 6. So b is 1. That's going to be part of my answer. Now, I'll do the same thing, except this time I want to let x be a value that gets rid of b in my equation. I'll let x equal negative 4. If I do that, let x equal negative 4. And I can say 3 times negative 4 is negative 12. I'll get negative 12 is equal to a times negative 6 plus b times 0, of course. That's giving me negative 6a is equal to negative 12. Thus, a is 2. Now, I have a is 2, b is 1. This integration problem, I'll go up here to the very beginning and say all of this integration problem is simply equal to the integral of a over x plus 4, where a is 2. So I'll say 2 over x plus 4 with respect to x plus the integral b. So I'm using this partial fraction to represent this function as two separate functions. So plus b 1 over x minus 2. And I know that the sum of these two integrals is the same thing as the original integral, but these two are extremely easy to integrate because in both cases I can say, do I see the derivative of the denominator and the numerator? Yes. This one is 2 times the derivative of the denominator, so that's going to be 2 natural log of x plus 4. Plus natural log of x minus 2. Plus the constant of integration. Final answer. Last problem on here. The only thing that separates number 13 from number 14. Number 14 is I have what's called a repeated linear factor in that denominator. The x squared could be written as x times x. It's really, it looks like a quadratic factor. It's really a repeated linear factor because it could be factored as x times x times x plus 1. A quadratic factor that's not a repeated linear factor would be something like x squared plus 1. You can't factor x squared plus 1 in the real number system. That would be what's called an irreducible quadratic factor. Totally different technique to solve that problem. This one, though, we'll say we have the integral of x minus 5 over our x squared times x plus 1. We're integrating this with respect to x. So just like the last problem, it's more of an algebra problem than it is calculus. You break it apart and say, can we use partial fraction decomposition to rewrite this as something easier to integrate? Right now, there is no technique of integration we have that can solve that problem. It does not exist. So we simplify it and say, well, this is equal to a over x plus b over x squared. You'll have a separate fraction for every single power of that. If this would be in an x cubed, I'd have a over x plus b over x squared plus c over x cubed. Plus c over x plus 1. So now, in simplifying this out, just like last time, I'll multiply by the least common denominator.
You wouldn't cube the x plus 1?
No, it's just x plus 1 to the first.
But if it would say it was x cubed in the very beginning one, then it'd be c over x cubed plus d over.
D over x plus 1, if that was the case. Yeah. So, in this one, my least common denominator is just this group over here, x squared times x plus 1. I'm taking an x squared and an x plus 1, multiplying it into all of the terms in here. Of course, I'm also multiplying it on this side. When I multiply it on the left, I just get x minus 5. And I think there was some confusion last class about exactly what canceled on this side. I'm trying to make sure I show it a little better right now. I know when I take this a over x term, multiply by this least common denominator, yeah, x is going to cancel out one of these x squareds, but I'm still going to have a times x plus 1. Plus, here, b is over x, that x squared is going to cancel out the entirety of that factor of x squared, so I'll just be left with b times x plus 1. And I know that this x plus 1 will cancel this x plus 1. I'll just be left with c times x squared. Okay, now let's see. What I would do with this is I'd say, okay, in order to get rid of both the a and the b term, I would let x equal negative 1. If x is negative 1, then your left-hand side is negative 6. And you'll have a factor of 0 here and a factor of 0 here. So you have no a and b in your equation. And you'll get c times negative 1 squared. Well, that's c times 1. So you would say we can see that c is negative 6. And then for the next one, I could say, okay, I was able to cancel out the a and the b term by letting x equal negative 1. Please also notice you could cancel out the a and the c term by letting x equal 0. So I'll say, okay, if I let x equal 0, my left-hand side is just negative 5. My right-hand side, I'd have a times 0, c times 0. I'd have b times 1. So I get b is negative 5. So I know c is negative 6, b is negative 5. I don't know what a is. but I can say it's going to be easy to find out. If I ask you, what's the coefficient of the x squared term on the left? What would you say? Yeah, there is no x squared term on the left. So I'd say the coefficient of x squared on the left is 0. So I'll say, okay, 0 equals. Now I would ask you, what will be the coefficient of an x squared term on the right? And I don't think you should have to multiply it all out. We should be able to see it from just what we have here. B will not be a coefficient of x squared. There's no x squared, it's multiplying. B will be a coefficient of x and a constant. Over here, though, I would have A is going to be a coefficient of x squared. C is going to be a coefficient of x squared. So the coefficients of x squared on the right-hand side would be A plus C. I know I need the coefficient of x squared to be 0. Well, it's A plus C on the right. So in other words, A plus C needs to be 0. And I already know that C is negative 6. So I can say 0 equals A plus negative 6. So that's the same thing as A minus 6. Add 6 to both sides. A equals 6. So now my original integration problem, bring it down here and say the integral of x minus 5 over x squared times x plus 1 with respect to x is equal to a over x, 6 over x, so I'll say the integral of 6 over x with respect to x, plus the integral of b over x squared, where b is negative 5, plus the integral of c, negative 6, over x plus 1 with respect to x. Please don't lose any points because of poor notation, not putting the dx with each of those. That'd be terrible. I'd feel guilty if I kept my points, but I probably would. So now, whenever you go in and do this, you'd say, well, the first and the last one are simple. They're just natural log. The derivative of the denominator is 1, so the numerator is simply a multiple of a natural log. The middle one, a little harder. So I'll go ahead and say, well, the first one is 6 natural log of absolute value of x. The second one, I'm going to pull that minus 5 on the outside and say it's minus 5 on the integral of x to the negative 2 with respect to x. And my last one, that's just minus 6 natural log of x plus 1, since the derivative of the denominator was in the numerator, times negative 6. So this middle one is the only one I need to work with. And I can say, well, I know x to the negative 2 is the same thing when I integrate as x to the negative 1 over negative 1, which is the same thing as negative 1 over x. So this middle term is just going to be a negative 5 times a negative 1 over x, which makes it plus 5 over x. So I'll say 6 natural log of x plus 5 over x minus 6 natural log of x plus 1 plus the constant of integration.
Did you not combine the 6L and x and the other 6L?
Oh, I like the way you're thinking. Great. You normally don't want to do stuff like that. Okay. Okay.
I'll just double check that you feel
yeah, since you had, let's say you have to. No, I'm just kidding.
Just for a second.
So this is the natural log of x to the 6th. How would I? Oh, well, it's just minus. Boo. Then I'd say, so this is going to be the natural log of x to the 6th over x plus 1 to the 6th. And then I don't even need the absolute value anymore because anything to the 6th power is automatically positive anyway. So it's just the natural log of x to the 6th over x plus 1 to the 6th plus 5 over x plus c. I'm glad you asked.
I'll just double check and make sure I wasn't.
No, I think that'd be a fantastic idea.
You could put 6 as a coefficient to the natural log of that.
You could, and just, yeah. Actually, I think that would look nicer. Yeah, it would.
You do that.
Say that again.
Number 13.
I still didn't hear you, Susan.
Number 13. How we see
Oh. Yeah. So you'd say, so in 13 you'd say it's the natural log of x plus 4 squared times x minus 2. And then technically you'd need an absolute, because that could be negative, so absolute value around it plus c. Yeah.
I was going to ask you, did you see something?
Now, did you notice, and I did not do it because I didn't like what the book did, but in section 7.3 specifically, if you looked at their solutions and you looked at mine, like, wait a minute, his solution looks quite a bit more complicated than theirs. Whenever they had a natural log that had like square root of x squared plus 9 over 3 minus x over 3, something like that, plus c, they went ahead and said, oh, that whole numerator is divided by 3 inside of a natural log. So they said, that's nothing more than minus natural log of 3, which that can be absorbed by your constant of integration. So they would have said, this is just the natural log of the absolute value of the square root of x squared plus 9 minus x plus c. I didn't like that. I mean, it just kind of bugged me. It's correct.
It just seemed like they canceled out something.
No, they're not canceling out. Well, other than they're saying it's this.
Yeah.
And they're saying that's just a constant anyway, so just absorb it.
I think
as a
sometimes
C.
they actually showed the 3 dividing the C.
Oh, did they?
Yeah.
Did they do any C1, C2, C? That bugged
Yeah.
me. Oh. I don't like